Hey physics friend, Mr. Collier here. We are going to talk again today about dynamics. We're going to talk about revenge of the force. We're going to talk about something called impulse. First, I want to talk about a quick review of momentum. Momentum is really moving inertia is a way to think about it, right? The mass of an object, its resistance to motion, is called inertia. And that mass times velocity is what we call momentum. So it's really just inertia in motion. So the product of mass and velocity is what we call momentum. So if you can look at a couple different objects, say a big giant ship has a very large mass, but it's not moving very fast, and the product of those would be its momentum. And you can look at a different object, like say an astronaut. On the International Space Station, they orbit the Earth every 90 minutes, so only an hour and a half to go around the entire Earth. So while an astronaut might have a very small mass, they're moving very quickly, very large velocity, and so there's still a lot of momentum there. It is a vector quantity, which means that direction is going to be super important as you do your calculations. And its units are going to be kilograms times meters per second, right? The units for mass times the units for velocity, kg/m/s. Now, Newton's second law can actually be put in terms of momentum, so let's take a look at that. The force on an object is equal to its mass times its acceleration. Well, acceleration is defined as a change in velocity over time. And, oh, hey, look, mass times a change in velocity, that's the definition of momentum. So we can actually write that the force is equal to the change in momentum over time. And if we rearrange that equation, we can actually see another one show up. That force times time is equal to a change in momentum. So this is actually going to let us talk about something called impulse. So this is the equation from impulse, but if you look, it's not really anything different. All we've done is rearranged momentum, and we're simply talking about a change in momentum. So when we say the word impulse, we're really just asking you how much has the momentum changed of an object. So impulse is kind of similar to momentum, the way work is a change of energy, right? So if I do work on an object, I change the energy of that object. If an object experiences an impulse, it has a change in momentum. They're very analogous to each other. An important difference, though, is that impulse is a vector quantity. It's not scalar like work and energy are. The units for impulse are going to be 1 Newton times 1 second, right? So you're applying a force over a certain amount of time. But if, again, like I showed you in the last video, if you dissect that unit, it's really the same thing as a kilogram meter per second. So, as I mentioned, momentum change is the same as impulse, and so they use the same units. All right, let's talk about how the third law applies to impulses. We're going to talk about collisions, and you're actually going to do some problems with this in our next section, but I want to introduce it now. So every action has an equal and opposite reaction. That means when two objects interact, they experience equal and opposite forces. Now, every action and every interaction are going to take place in the same amount of time. They take the same time. So the times are equal, which means that every impulse, force times time, has an equal and opposite impulse. Which also means that every change in momentum is equal and opposite. We're going to look at this as we start to do our calculations with momentum change and impulse change. So, whatever momentum the first one has plus the second one is going to add up to 0. So what are some applications of impulse? Well, if we look at an object that's moving, it has momentum. And for it to come to a stop, it needs to go to 0 momentum, right? 0 velocity. And so it can change that momentum by changing with a small force over a long time or by a very large force over a short time. Either of those will be an impulse that brings its momentum to 0. And of course, from a safety point of view, you want that impulse to have a small force over a large time. So most safety devices are trying to help you spread a force out over a longer time to allow you to change your momentum. Airbags, seat belts, crumple zones, bumpers, padding, highway barriers, these are all things that during an impact make it take longer for the object to come to a stop, therefore needing a smaller force, therefore being safer. Even things like having cushions in your shoes just allow the impact of your feet against the ground to take a longer time to slow your foot down. If you jump, when you bend your knees when you land as opposed to landing stiff-legged, it doesn't hurt as much because you're getting a longer time and hence smaller force to change that momentum. This can show up other places in sports as well, like if you roll with the punch. In boxing, you will experience a smaller force over a longer time, or even in sports like golf, baseball, tennis, your coach very often tells you to follow through. Why are you following through? Following through allows you to keep a larger time that your bat is in contact with the ball, for example, and that imparts larger momentum change on the object, and hence it's going to be leaving at a faster speed. One last thing is that when you look at a graph of force over time, the impulse is going to be the area under the curve, right? And so that is impulse. It is a change in momentum. When something has momentum and that momentum changes, again, from a force, you're going to have an impulse. And you can calculate it by multiplying the force times the time, or simply the change in momentum. Good luck. Here's a real quick sample problem with impulse. Say you're hitting a 47-gram golf ball. You impact it for 1.5 milliseconds, giving it a speed of 75 meters per second off the club head. How much force does the club push on the golf ball? So first we want to convert our mass to kilograms. When you're doing any impulse calculations, you need your mass to be in kilograms. From there, I'm going to figure out the force equals the time. Force times time is equal to the change in momentum, mass times a change in velocity. Now I can sub in my numbers, and I get my force times my 1.5 milliseconds is equal to the mass times its change in velocity. And so that is a very common way that you're going to set up some problems, looking at how the force times time is equal to the change in momentum. That is the definition of impulse. Good luck with the next homework, 6-2.